Let's pause for a second and zoom out. This simple equation gives us two powerful controls. One control lets us move the line up and down. The other control lets us tilt the line left or right. That's it. That's the core idea. With just these two adjustments, we can draw any straight line we want. Now, when we place this line on top of our data points, the line starts making predictions. For a given house size, the line tells us what price it thinks makes sense. But drawing a line is not enough. Some lines will be close to the dots, some lines will be far away. So the next question is obvious. How do we know if a line is good or bad? To answer that, we need two things. First, a way to measure how far the line is from the data points. And second, a way to compare different lines and decide which one is better. That's where the real math begins. Next, we learn how to measure error, one point at a time. And once we can measure error, we can finally teach the model how to improve. This is essential for all of you aspiring data scientists. It is important to understand how to check for errors in the data and to persistently enhance accuracy of the line until the desired objective is achieved. To answer that, we need a way to measure how wrong a line is, point by point. That's next. Now that we can draw a line, let's answer the most important question so far. How wrong is this line? Because a line that looks okay can still make bad predictions. For any house size, the line gives us a predicted price. This value comes directly from the equation. This is what the model thinks the price should be. But we already know the actual price from the data. The difference between the actual price and the predicted price is called the error. You can think of it as the vertical distance between the dot and the line. If the line predicts too high, the error is negative. If the line predicts too low, the error is positive. Either way, the error tells us how wrong the model is for that point. But a model doesn't make just one prediction. It makes predictions for every data point. So we don't just have one error, we have many. Some small, some big. Here's the problem. One line might be very wrong for one point, but good for the others. Another line might be a little wrong everywhere. Which one is better? We can't answer that by looking. What we need is a single number that tells us how bad a line is overall. A number we can compare across different lines. Lower number means better line, and that's exactly what we'll do next. We'll combine all these errors into one value, the loss. That's where learning really begins. So now we have a bunch of errors, one for each data point. But we still don't have a single way to judge how good or bad the line is. We need one score. You might think we can just add all the errors together. But there's a problem. Positive errors and negative errors cancel each other out. A very bad line could end up looking perfect. So instead, we square the errors. Squaring does two important things. First, it makes all errors positive. Second, it punishes large mistakes more than small ones. For each point, we take the actual value, subtract the predicted value, and then square the result. Now every mistake counts. Finally, we take the average of all these squared errors. This gives us mean squared error. One number, one judgment. Lower MSE means the line fits the data better. Higher MSE means the line makes worse predictions. Now we can compare lines objectively. This is the score the model cares about. It doesn't know about dots or graphs. It only knows one thing: reduce this number. So now we have a way to measure how bad a line is. The final question is, how do we change the line to make this number smaller?